Chapter 5, Section 3 on inverse functions. Now, part of this section is actually just a review of some things that we talked about in pre-calculus involving inverse functions, and then part of it involves the calculus. So we'll do some review first, but the reason that we're covering this section is because even though in the last two sections we discussed the natural log, we want to also be able to differentiate and integrate the natural exponential functions because of the many applications that they have. And those functions are inverse functions of the natural log function. So what we're going to do is review a little bit, and then we'll pick up a couple of theorems that will help us out with the calculus. All right, first things first. What's an inverse function? An inverse function, a function g, is an inverse function of a function f if f of g of x is equal to x for every x in the domain of g, the interior function, and g of f of x is equal to x for all x in the domain of the function f, again the inside function. So if we compose them in both orders and we get the identity function I of x is equal to x, then, and this is true for the domain, then we have inverse functions. So that's the way you prove it by definition. If they say prove that these two functions are inverse functions of one another, that's how you go about to show that with by definition. So remember, if g is an inverse function of f, f is an inverse function of g. They're unique. The domain of the inverse is equal to the range of the original function, and of course the range of the inverse is equal to the domain of the original function. Now notice here the notation with the -1. You may remember that being from your algebra days and your pre-calculus days. That does not mean to the -1 power, that means the inverse function of f. Okay, now it says a function may not have an inverse function, because not all functions do, only one-to-one functions do. But if it does have it, as I mentioned before, it's a unique function. So let's show in this example here that these two functions are inverse functions of one another. So the first thing I'm going to do is I'm going to take the composite f circle g of x. This is f of g of x, which is f of, now g of x is the cube root of x minus 2 to the 4th power. Now I'm going to substitute that in for the rule there, in for x, in for the outer function f. So that would be 4 times that expression to the 3rd power. That's the cube root of x minus 2 over 4. Okay, plus 2. And so what happens when you cube a cube root is you just get the radicand. And these 4's cancel, so I have x minus 2 plus 2, and of course that's equal to x. So let's try it the other way around, g circle f, because sometimes it works in one direction, but it doesn't work in the other way. The composite operation for functions is not commutative, necessarily commutative. So let's take g of f of x, which is, let's see, 4x to the 3rd plus 2. And I'll substitute all this into the rule for g, in for the variable x, and I get the cube root of, in for x there, all of this. So that would be 4x to the 3rd plus 2 minus 2 all over 4. Well, this is the cube root of, as you can see, the 2's cancel. So I have 4x to the 3rd over 4. The 4's cancel, so I have the cube root of x to the 3rd, which of course is x. And so it works in both ways. So show that they're inverses. Therefore, by definition, f and g are inverse functions. All right. Now, there's a theorem here called the reflection property of inverse functions. And this has to kind of do with graphs of a function and its inverse. The graph of f contains the point a, b, if and only if the graph of f inverse contains the point b, a. Now remember, when you reflect the graph of a function in the line y equals x, you get its inverse. Now it might be an inverse relation, but if you have a one-to-one function, it's going to be its inverse function, and you can reflect it by interchanging the x and the y values of the ordered pairs. This is since one-to-one functions are so important. Remember, one-to-one functions can be determined by using the horizontal line test. It got kind of cut off there. Sorry about that. That's supposed to say horizontal line test. And the horizontal line test shows that it's either always increasing or it's always decreasing. Monotonicity. Oof, There's a good hangman word right there that shows that it's always increasing or always decreasing. So if you have a one-to-one function, it's going to have an inverse, and the graph of the inverse function is going to be a reflection of the original function in the line y equals x. Here's another review theorem. It says the existence of an inverse function. A function has an inverse function if and only if it is one-to-one. For every x, there's exactly one y. For every y, there's exactly one x. And the function f is strictly monotonic or monotonic. I'd have to look it up, but I always call it monotonic because it kind of sounds neat. On its entire domain, which means it's always increasing or it's always decreasing. Okay, that's what it means. Then it is one-to-one and therefore has an inverse. So I have a couple of examples here that I'm going to see whether or not these functions have an inverse function. Now, one way that you could do this is you could graph this and then determine if it passes the horizontal line test. But your graph is only as good as you're able to plot points, and sometimes it might not look like it's one-to-one, and it is, or vice versa. So what we can do here is get Mr. Calculator out and hope that it's distinctive enough. So let's see, which of these functions has an inverse function? Well, the first one I'm going to look at here, the one that's highlighted, that's our, here, let me move it over a little bit. That's answer A there. I'm going to go ahead and graph that one. And notice what I get. That looks like it's going to pass the horizontal line test. It does not look like any horizontal line is going to intersect it in more than one spot. Well, let's prove this. Let's take the derivative, because the derivative is where we find if it's increasing or decreasing. And the derivative is 3x squared plus 2. Well, you can see here that 3x squared plus 2 is always greater than or equal to 0. Because no matter what you plug in for x and you square it, it's non-negative, and then you multiply by 3 and it's non-negative, then you add 2 and it's positive. This is always going to be greater than 0. So this is going to, yes, have an inverse function. Okay, because the derivative f prime is always increasing. All right. Now on the second guy over here, it looks very similar. I just changed a couple of the signs here. Let's determine if g has an inverse function. So let me go back to my let's see if I can get this here first off. This is just wonderful here. All right, now here's the second function here. Let's go ahead and push its graph. Oh, no. It looks definitely like it would fail the horizontal line test right up here. It looks like it could draw a horizontal line that would intersect it more than one point. Let's take the derivative. So I'm thinking this one's a big no. But a graph, as I mentioned before, is not always the best way to go about it, especially if you don't have the your window set up right. So I take this. I said 3x squared minus 2 greater than or equal to 0, which would mean that 3x squared would be, let's see how I want to put this. Let's do it this way. Let's see. Let's go 3x squared minus 2 is equal to 0. I get x squared equals plus or minus the square root of 2/3, which is plus or minus the square root of 6/3. So what happens here is on my number line for g prime, if I put negative square root of 6/3 and positive square root of 6/3 and test my interval, take a number from here, let's say 0, and put 0 in here, it's negative. Take a number over here like 10, plug 10 in, it's positive. Well, you can see right here, this will be positive as it turns out. This is not strictly monotonic. Okay, so no, I didn't leave myself enough space. No, it does not have an inverse function. So don't just show the work, make sure that you answer it as well. All right, now, to actually find an inverse function of a function f, provided it's one-to-one, I always have followed these same rules that I show in algebra and I show in pre-calculus. Interchange the x and the y, solve for y. And then, of course, you're going to have to define the domain of whatever your inverse function is to be the range of the original function f. So in this case here, my domain here for this function g is such that I have to make sure that 4x minus 2 is going to be greater than or equal to 0, which means that x is going to have to be greater than or equal to 1/2. So the domain of my function here, g, is 1/2 to infinity. The range, never leave myself enough space, of this, I can't get this to be negative, but it can be 0 or any positive number thereafter, so my range is going to be from 0 to infinity. Now, let's go ahead. I'm going to change g of x. I'm going to write it as y equals the square root of 4x minus 2. Interchange the variables. Square both sides. Add 2 to both sides. Divide by 4. I'm going to write this as x squared plus 2 all over 4. And this is what I'm going to call my inverse function. Now, if you look at this, and you say, well, that's a parabola. A parabola is not going to be a one-to-one function. A parabola is going, in this case, it's going to open upward. Well, that's because I have the restriction here on the domain. Remember, the domain of the inverse has to be the range of the original. So this is for x greater than or equal to 0. And that would only be 1/2 of the branch of the curve of the parabola. All right? So that's how you find the inverse. If it's in function notation, change the f of x, g of x, h of x to y, interchange the variables, and then solve for y. When a function is not one-to-one, we can sometimes, and usually we can do this, we can restrict the domain of the function to make it one-to-one. So one of the themes that we're going to be looking at later on in this chapter are inverse trig functions, because we know, for example, y equals the sine of x. That is certainly not a one-to-one function here. In fact, I'm just going to kind of be really messy here. It's going to kind of do something like this, where you get that wave. So what we've done with define an inverse sine function, and you may remember this from your pre-calculus days, is we restricted the domain to be between negative pi over 2, oops, and pi over 2. Because only this part, let me get my color pencil here, would pass, there we go, would pass the horizontal line test. All right, and we can have inverse functions if we restrict the domain for the 6 trig functions. All right, now here's the first of the 2 theorems that we're going to mention here that have to do with inverse functions and calculus. The first one's talking about continuity and differentiability, which we talk about, of inverse functions. It says let f be a function whose domain is in the interval I. If f has an inverse function, then the following statements are true. If f is continuous on the function, f inverse is continuous on its domain. Excuse me, on its domain. I said on its function, on its domain. If f is increasing on its domain, then f inverse is increasing on its domain. If f is decreasing on its domain, f inverse is decreasing on its domain. And if f is differentiable at c, where f prime of c is equal to 0, then f inverse is differentiable at the y value at f of c. Now, these are all good things to know, but the one that shows up on the AP test is this theorem, the derivative of an inverse function. It doesn't show up every single time, but it shows up enough to keep track of it. And the derivative of an inverse function says, now this is, you're finding the derivative or information about the derivative of a function, not knowing its inverse, just knowing that it does have an inverse. That's kind of neat. It says let f be a function that's differentiable on the inverse, on the interval I, and if f is an inverse function, has an inverse function g, then g is differentiable at any x for which f prime of g of x doesn't equal 0. Moreover, like that word moreover, g prime of x, now we don't even know the inverse function, we just called it g, is equal to 1 over f prime of g of x, as long as f prime of g of x doesn't equal 0. So we're going to try an example of that and see what happens here. But what happens, unfortunately, is that if we were trying to find the derivative of an inverse and it's not convenient to find the inverse function, we interchange the variables and it's difficult to solve for y, then we can kind of bypass that by using this theorem. Now this would be a tough one. If I interchange the variables, if I call this guy here y and I switch the variables, I would get x equals y to the third plus y minus 1. And I don't know the algebra off the top of my head how to go about that to solve for y. It is a one-to-one function and it does have an inverse. I just don't think I can find the rule. So what I'm going to do is first, I'm going to find f inverse of 9. Now if you look at this, you say f inverse of 9. I don't have f inverse. How can I plug 9 in? Well, whatever f inverse of 9 is, let's call it, I don't know, c. That means if I plug c in for x, I would get, in the original function, I would get c to the third plus c minus 1 is equal to 9. Well, I don't know how to solve this equation any better than I knew how to find the inverse function. But by trial and error, if I plug 2 in, I would get 8 plus 2, 10, minus 1, 9. 9 equals 9. So f inverse of 9 is equal to 2. So I did that by trial and error. Not the best approach, but I really don't have very many alternatives there. Now let's find, and this is going to the theorem here, let's find f inverse prime of 9. Well, according to this, this is equal to, I'll just get rid of that. This is equal to 1 over f prime. Now remember, g is the inverse in the theorem here. So this would be f inverse of 9. Okay, as long as this doesn't equal 0. Well, just a minute ago I found that f inverse of 9 was 2. This is 2. So now that gives me 1 over f prime of 2. Well, I need f prime. So back to here. F prime of x is 3x squared plus 1. So f prime of 2 would be 3 times 2 squared plus 1, which is 13. So this would be 1 over 13. So that's a little interesting there. And I have seen this problem on the AP, so you want to make sure that you take the time to practice a couple of these and also to make sure that you put this to memory. Now, there's a note here that I've written down. It says, at the point 2, 9, now remember, this is, the x value was 2, that makes it equal to 9, at the point 2, 9, okay, that f prime of 2 was that the slope of the graph, the derivative, was equal to 13. But at the on the inverse function at 9, 2, the slope of the graph of the inverse is 1 over 13. Notice reciprocals. So dy dx is equal to 1 over kind of dx dy is the way we would write it, because you've interchanged the variables and you're taking the derivative. So let's try one more of these. These are a fun time. Now again, one-to-one function here, and I want f inverse prime of 2, which should be 1 over f prime of f inverse of 2. Now I need to know what f inverse of 2 is. What would I plug in that would give me 2? Well, it looks like, just by trial and error, f of 1, which would be 3 times 1 cubed plus 1 minus 2 would equal 2. So this is the 0.12 on here. F inverse of 2 then would be equal to 1. So what I'm going to do is I'm going to go ahead and plug 1 in here. So this is 1 over f prime of 1. Now what's f prime of 1? Well, I have to take the derivative. That would be 9x squared plus 1. So if I plug 1 in here, f prime of 1 would be 10, and this would be equal to 1/10. All right, so look these over. We're going to, in the next section, talk about the natural exponential function, which again is the inverse of the natural logarithmic function. So a little bit of review on inverses, and then this key theorem right here, definitely worth your while to take the time to practice, practice, practice.